This lecture is going to go over modeling complex data and relationships between variables, so it'll touch on topics relevant to both readings this week. So first, I'll talk about piecewise function, and this is a kind of model that we can use when there is variance in how a particular data set behaves at different points in time. This is particularly relevant for the reading looking at the impact of COVID-19 on reading performance. They use piecewise functions to describe the relationship, or rather rate of change that they see in their results. So, as we've mentioned previously this semester, statistical models always have assumptions about the data that goes into the math that happens in the statistical model. And we need to make sure we meet those assumptions to appropriately use that particular model. So a linear model assumes that there is a linear rate of change, so that whatever change in one variable, variable x, is proportional to the change in y. And if I were to put that data in a graph, I would see a pretty linear looking line in my data. It wouldn't be curvy, it wouldn't be any other weird shape, it would just be a line. The logistic or exponential models, which we've also seen, you can think of the S-shaped curve one, has a assumption that the rate of change depends on where in the data set you are, but your rate of change, even in that change of the rate of change, is predictable. So you know that if you're in a logistic curve, you'll start out slow, and then you'll increase, and then you will eventually taper off again. It's predictable. Same for the exponential. It would start off slow, but as it gets further and further on, the rate of increase gets exponentially bigger. So the only difference between the linear and logistic and exponential is just the shape, but they're all consistent in one kind of mathematical equation. But if your data doesn't fit into any of those, then you might use a piecewise model. So you may have been thinking that word might sound familiar in that kind of ghost feeling in your brain. If you recall way back to your algebra classes in high school, you probably were taught piecewise functions, where you were given a series of functions, so short little equations, and then you plotted them to have 3 or more different angled lines that may or may not have connected to each other. So to refresh your memory, this is what your piecewise function looks like. So that piecewise function, it's an algebraic function. So you're plotting multiple different lines on the same graph. So we've got this graph right here on the right. There's two functions. One that starts way down in the bottom, the blue. I'm trying to grab my thing. So this is one function, and it tells us when this function is relevant. So there's a particular parameter here. And then once our x value changes, so our x-axis here, once it changes to larger than 0, so we've got our new parameter over here, our line shifts. So our data starts down here, and then it goes up here at the 0 point on the x-axis, where 0, 0 is our coordinates here. So this is, in general, the principle that we'll be working with when we're thinking about how they use the piecewise function in the data for that article. So we can have circumstances in education research where piecewise functions are relevant, and one of them is the reading that we had this week, because they noticed that the rate of change for the students varied depending on what time point you were comparing. So this is the graph that they had in that, or one of the graphs, graph B, that they are looking at the reading scores. So there's a lot that's going on in this graph, but I'm going to break it down. So first things first, we have a key down here that we want to pay attention to because it tells us what each of these lines means, or rather who these lines represent. So the gray lines are students who are English fluent. The dark lines are the English learner students. So that's our first categorization of English fluent and English learners. Then we also have the shapes for the dots. And the dots are when they took particular time points when they were getting those scores for the map reading assessment. The triangles are for students who were in person and remote, but they're using the same symbol to also keep the grouping together. So the symbols aren't changing based on the English fluent versus English learner. The symbols help us, along with the color, to distinguish who is who in this data set. And then we do have a distinguisher that goes across our two groupings, and that's the dashed line versus the solid line. So the dashed line, which we've got one up here and one here, those are the students who had remote instruction. The solid lines are the ones who had in-person instruction. So this key is really important because it's telling us for each data point or each line who the students are in that particular line. So whose data are we looking at? So when we look in this graph, we've got 4 different sets of data based on how we're grouping our data down in the key. Now, you may notice the lines don't look very straight. This one is kind of straight, but it's got a little bit of a bend to it when I go from this point to this point. This one changes direction, so it's kind of going up, and now it goes sort of down, a little flat. We see a similar one for the dotted up here, and this one's the only one that looks like it actually, if I got the equation for it, it would be the same equation basically on both sides of this point. So we only have one line that actually is linear looking. So there's only one line that if I was to ask, my program to give me the equations for these lines, and I told it to use a linear model, it'd only be actually accurate for this one group of students up here, because they had a consistent rate of growth from fall to winter and winter to spring. But if I told that model, or told it to use the same model for these other 3 lines, it actually wouldn't correctly give me the rate of change or rate of growth for these students. Because for some, they actually got a little bit faster, or got a little bit better faster going from fall to winter than winter to spring, or they were improving and they either plateaued or almost plateaued or started going down a little bit. So if I used a linear model, it would try to average itself in between all of the data, which would introduce a bunch of error when I've got these points where my angle changes. So here, they use the piecewise function because it's most representative of what's happening when teaching format seems to be really important, where if you're in the remote sections, you have a negative rate of change, so a negative growth rate, in winter to spring. And the piecewise function helps them capture that component, because it's not true from fall to winter. And it doesn't mean that their data is bad, it's just this is what the data is. And so they need to capture that they did have a positive rate of change from fall to winter, but then they had a neutral to negative rate of change, depending on which group you're looking at, from winter to spring. So the piecewise essentially lets them have an equation that represents this part of the line, and then another equation that represents that part of the line. So it's better fitting their data to the behavior that they're seeing, rather than trying to make their data fit a particular model, like just a linear model. The other thing that I do want to mention is that these lines, particularly here, but also if you imagined that these continued in their trajectory, they would eventually cross somewhere out here. These actually do end up crossing. When we see that in our data, we call that an interaction, and we'll talk about that in a moment. So why would you do a piecewise model over another statistical model? Well, I kind of hinted at it before. You want to be the most accurate you can. So we don't want to violate any assumptions of a statistical test. If my data isn't linear, I don't want to use a linear model because that violates the assumption. And that's just going to introduce a bunch of error into my results. And I want to be as low in error as I can. Usually you can't get to 0 error because there's just some amount of randomness that happens in the universe. But Ideally, you want to do what you can to reduce the amount of error. And one of the ways we can do that, besides good experimental design to begin with, is making sure when we're doing our statistical tests that we're picking the ones that are appropriate for our data. And you might see this talked about a little bit, especially if you end up taking other research-related classes or maybe statistics. We talk about error in two different ways. So one way you can have error, and this could be because you use a not appropriate test, is that maybe you find a statistically significant result, but your data isn't actually statistically significant. So we call that a type 1 error, or a false positive. The positive being finding that it's statistically significant when it's not actually true. The other way we can have an error is that maybe we don't find a statistically significant result, but actually there is one. And so that's when, we call that a type 2 error or a false negative, where technically it's giving us a negative result that it's not statistically significant, but it actually should be. And both of these can happen because the thresholds that statistical tests use to decide when something is statistically significant or not can be influenced by the amount of error that is present. So if you're using a test that's not made for your data, it's going to increase error, which increases your chances that you have either a type 1 error or a type 2 error, depending on what your data looks like. So ideally in methods, we look for them telling us that they have checked their data to know what the behavior of their data looks like, to know what statistical tests are appropriate. So that's when we see them talking about things like checking for normalcy. So does it look like a bell-shaped curve? Are there weird skews to the data? We might see a test called homogeneity of variance. That's a weird word, which essentially means when we are comparing across data sets, do we have similar amounts of variance, or are some data sets really spread out and some are really, really tight around that mean? That can impact how statistical tests work. They can also just plot their data to show you what it looks like as well, though ideally they are doing tests, statistical tests to test the behaviors of their data. Because we like numbers. If we're using numbers, we want to have the numbers, but we can also look at it visually as well. Now, you don't really need to know how those tests work, but it's rather knowing what the researchers are using them for so that you know if the researchers did a high quality analysis or not. If they're doing these checks with their data, it tells me that I can at least trust their data a little bit more and trust their analysis because they've taken the time to ensure they've done an appropriate analysis for their data. It doesn't mean that articles that don't do these are useless or not good, but I want to be a little bit more cautious if I don't have this information to know that the authors have taken the time to evaluate their data to choose tests appropriately or not. So some things we might look for in the methods section to evaluate, have the authors done these kinds of tests? There's many tests developed, and occasionally I find ones that I haven't heard about before. But they should be telling you what the test does. So at minimum, even if you don't know the name of the data or name of the test itself, they should be telling you why they're doing that particular test. So you want to be looking for, when they're talking about their analysis, are they talking about the checks they did, whether it's check for normalcy, checks for homogeneity of variance, checks for skewness, checks for kurtosis, which is another way the data can kind of be funky. And based on those tests, they should then tell us why they then made subsequent decisions. So why they picked particular models, if their test told them that their data was non-parametric, so their data isn't normally distributed for some reason, and they tested to tell us that, then they use the appropriate non-parametric tests versus using the parametric ones. So if you remember way back at the beginning of the semester, we've read that article that did both the parametric and non-parametric tests together, because when they visually plotted their data, it didn't look particularly off. But when they ran the tests to check, they were actually just enough to trigger those tests to suggest that their data wasn't parametric. And so they did both to be safe. So you'll see them checking for normally distributed data. If the data is skewed in any way, we should see homogeneity of variance, like I said. And that's if they're comparing different groups, so experimental versus control. Maybe they have multiple experimental groups. They should be checking. And if their data is linear or not, because again, if their data isn't linear, they shouldn't be using a linear model. So now that we've talked a little bit about choosing tests, the other thing I want to talk about, which happened in both of the articles that we read this week, is interactions in our data. And these are things that we have encountered before, but I haven't really dug into them yet, so we're going to go through them now. In particular, because both of these articles really highlight what is happening in their data by the interactions that appear. So when researchers are doing those huge mathematical models and they give us those tables with a lot of information, where they're showing us what variables they included in their model, they usually include interaction terms, whether they're testing for it just to see if it's there, or they have some assumptions that there might be interactions that are going on. So what does an interaction term do in these models? And that's usually what we'll see it called as an interaction term. And that is telling us two or more variables that they're looking at together at the same time. So for whatever variables I include, at minimum you need two, because you need two to interact, but you can have three as well. I want to look at specifically when I include those variables together, does it impact a given data point? So rather than looking at my data one variable at a time, so looking at it, English language learners versus English fluent students, I can make an interaction term by having English proficiency and modality of learning. Did you do remote or in person? So because I have those two together, it becomes an interaction term. So what would this look like in a paper? Well, we saw this twice in both papers. So in the article and reading achievement, which is the one I was just talking about, those interaction terms were how they were explaining what was happening for the students based on both their English learning status or English fluency status and the modality that they were taught in, and how both of those together impacted their grade, their reading performance. So when those two lines crossed over, that indicated there was a big interaction happening, that having both being an English fluent student but also being remote interacted and actually had a different score than if you were English fluent and you were in person. And so that essentially just summarizes a little bit of what I was saying, except that uses the English learner variable, but it did the same thing, where if you were remote, there was an interaction in terms of, for whatever reason, the performance went down in the spring semester compared to the other students who were in person. And in this case, you can compare across English fluent and English language learners. So there's different ways that you can kind of mix your variables to see what the impacts are based on the variables that you include. So often there's usually a handful of interaction terms rather than just one, because it is a combination of things. So another way that variables can relate to each other is what we call covariance. So when we're measuring multiple variables, often variables are changing at the same time, but they might be doing it in either similar or different ways. So if I'm just measuring a few independent variables, I might miss an important effect. So thinking about how many variables I'm collecting is kind of where we need to start here, where if I don't collect a whole lot of variables, then I might be missing an effect that I just am not accounting for at all in my data. So for our articles today, both of them, they had demographic variables as covariates. And essentially that just means they're using demographic variables almost as filters to see how the data changes based on which kind of group you fall in for the demographic variable. So for both of them, they were looking at gender. They also included ethnicity, One of them used GPA, the other, both of them also had socioeconomic status. These were all included in their models to see if they explained any component of the relationship that we were seeing. So if your covariates explain a lot of the variance, then it means the main variables you were collecting probably aren't actually the things that are driving that relationship. So in the study, if, say, for some reason, English language learner versus English proficient didn't have an effect, I probably don't want to be focusing on that variable because it's not helping me explain my data very well. But in contrast, if it is actually really impactful on my data, I might want to be focusing on it quite a lot. So researchers can figure out if their variables might be covariates by doing a series of models. And so when you see the tables where there's model 1, model 2, model 3, and the numbers kind of keep getting added on, that's them testing by adding a variable at a time to see how much it changes the explanatory power of the model. So you can kind of essentially isolate what variables have the most effect on the data. And finally, another way that variables might relate to each other is mediation and moderation. So because the world is a complex place, a lot of things can influence any particular outcome variable. Rarely do we have something that is a direct one-to-one relationship. And that's just because humans are complex and a lot of things influence what we do, how we perform, how we behave. So when a study says that a variable explains some amount of the variance, they're trying to see how much or how little, potentially, that variable impacts the other variable that they're looking at. So if it's explaining a lot of variance, it has a lot of impact. And sometimes variables by themselves might not, but when we make those interaction terms, the interplay does a lot of explaining. So within education research, we can look for those interaction terms because they can help us find if variables are doing a mediation or moderation behavior. And there is a distinction between those two, which I will talk about in a moment. So let's start off with mediation. So particularly for the second article, this was what they were looking at. So typically when we have a mediation, we often actually get figures to help represent the relationship. So thankfully with this paper we had the figure, but we will see this kind of what I call the 3 variable triangle, where we've got this kind of triangle shape here. And it usually goes from left to right. So we have our descriptor variable that ends up affecting another variable that impacts a third variable. And that's usually our outcome variable over here. So in this case, they were looking at that academic engagement. Now we know this is a mediation because it's like an alternate flow. So the mode of learning that they were in didn't actually directly affect the same day academic engagement. But there is a direct path that is statistically significant, because we can see those 3 asterisks right there, that we have a connection from your modality to your connectedness that you rated, and then your connectedness impacts your same-day academic engagement. So it's not a direct effect, but it is an indirect effect. And one of the main indicators of a mediation is the fact that it is an indirect effect, so that the relationship between your initial variable and your outcome variable isn't really strong, but you can make a pretty direct path through another variable. And so this variable right up here is your mediator. It is mediating the effect of your modality on same-day academic engagement. Now the other thing that we can have is a moderator. So in the case of the paper, they didn't find any moderators, they found mediators, but we see moderators happen in things as well. And so generally what we have is what I'd call the T-shape figure that they'll give us, where there are 2 variables directly connected, but there's a third variable that aims at the connection itself. So the variable is doing what we call moderating that direct relationship of the initial variable, so in this case, hours of study, and the outcome variable, exam score. So it's getting moderated by IQ here. So rather than it being that triangle shape, there's actually a direct effect that we have here, which is a connection that if they had statistics, we would see statistic significance between these two variables. So we need at least a medium. Sometimes it can be strong, this connection. And the IQ here would essentially act as a further explainer that would help us see the nuance in the data between this connection. And this is, I find, particularly useful when it's that medium connection where there's some connection, but it's not super clear. By including the moderator variable, it helps explain more than if I don't include this variable. So unlike the mediator, where I don't have a connection between these two at all, or it would be very weak. In the case of a moderator, there's already a fairly significant connection here, and it gets further explained when I include the moderator variable. So it's accounting for nuance. So essentially it's saying that already your hours of study impact your exam score, but when we include IQ, it has a more explanatory, the model is more explanatory of the behavior we see or the outcome we see with exam score when we account for a person's IQ. So not only does your hours of study matter, your IQ also impacts what ends up happening for that exam score. So often if there is an interaction present and it's pretty strong, one of the variables that's interacting is probably a moderator. It can depend, there are some different statistical ways they can test which one is the moderator, but in general, when you see that cross in the graph, you've got a moderator somewhere. So if we go back to that reading achievement article where right here we can see the cross because the solid line ends up going above the dotted line for the spring 2021 scores, there's also likely a little bit of a less strong but still potential interaction that happens for these two, but because there is different behavior going on, we can't really say for sure if the interaction is happening for the English learner students as much as we can see it for the English fluent students. So when we're looking at this graph, let's say that the English fluency state, so whether you're a learner, the light gray, or if you're fluent, the dark gray, or if you're a learner, the light gray, let's say that's my independent variable. So that's, I didn't change that. I'm not looking for it as my outcome. It's my kind of filter variable. And my score, the score you get on your reading test is my dependent variable. That's the thing that I collected data on. Then I would say that format of instruction is probably my moderator, because based on the crisscross I see here, the crisscross isn't happening based on color. The colors are actually pretty separate. So the language status isn't really telling me, or isn't doing any interaction with itself. But where I do see the crisscross of these lines is between the dotted and the solid line. So that is one way you can see which one's going to be the moderator. In this case, my moderator is going to be the format of instruction because it's going to eventually cross here. Also, if we imagined a trajectory, assuming they stayed at the same rate of growth, they'd probably cross somewhere out here as well. So I'm seeing a cross based on the format of instruction, but I'm not seeing the data cross based on if you were fluent or if you were learning. So that's one way you can parse out which one is the moderator in the graph. And so that would be all of my points that I just said there. Usually when we're looking at articles that are looking at mediators and moderators, or they are talking about it, they should be showing us the graphs. Sometimes they don't, but often they will. So you can actually see, okay, what variable is responsible for causing the crisscross compared to all the variables they're looking at in the case of this graph. So usually you can see when they're talking about a moderator, which one actually is the moderator.